Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about the Common Collector NPN BJT. Specifically, we're going to be solving for the input resistance, the output resistance, and the AV gain analysis of the small signal. If you want to pause the video and see if you can solve for these, and then come back to the video and see if you got the right answer, feel free to do so. We want to also note that the common collector is also called the emitter follower. Okay, and it's also common collector because in AC the collector is common to ground. So essentially, this is the collector. This here is the base, and this here is the emitter. Okay, so let's start with Rn and see if we can solve for it. So to solve for Rn says, the input resistance says, okay, let us find Vin over In when Vout is equals to 0. And in order to do that, we need to basically consider a wire at V0, or so a short. And so this is ground, so then this is grounded, so then this is 0 volts. Or essentially current is going to, in this node, we want to just flow through here. So no current will flow through here, and no current will flow through here or through here. So the circuit that I'm remaining with is just this Vin that goes through this R pi. And the voltage across here is called VBE, and this is Vin. And the current that flows here is In. As you can already see what Rn is going to be, but let's go ahead and write some equations. So for example, I'm going to write a KVL equation around that loop and say minus Vn plus R pi I times In is equals to 0. And then this becomes Vn is equals to R pi times In. And then again, this is Rn is equals to Vn over In, which is equals to R pi. So this is your input resistance for a common collector circuit. So let's go ahead and let me know in the comment section if you got the same thing or if you got something else. Let me know in the comment section. So let's go out and talk about the R out. So I went ahead and redrew the circuit, and the R out equation says R out is equals to V out over I out when Vn is equals to 0. So essentially what I'm going to do here is I'm going to erase this. I'm going to put a wire through it. I'm going to consider that there's a current flowing here in IO. And then I'm also going to realize something here. I'm going to realize that this is a node, and then this is a node, and this is ground. So this resistor and this resistor are connected in parallel. So I'm just going to go ahead and erase this RO and put it in parallel here with RE. And I'm going to consider the current that goes through here to be IOE, and the current that goes through here to be I pi. Now this current I pi is extremely small, especially in a BJT. So it's a lot of times we consider this to be around 0, but for simplicity or for exactness, we're going to consider it in this analysis, and then just take out the terms that have it when we write our final R out equation. So the first thing we want to do here is consider this loop, and we want to, and let me call this 1. We want to say basically that plus VBE plus, again, last thing I forgot to say was that the drop across this resistor is also VO, right? Because it's in parallel with this one. So first BBE plus VO is equals to 0. And as a result of that, VBE is equals to minus VO. I can write an equation for IO. So let me do this. My second equation, I could say IO is equals to IOE because it's leaving the node minus GM VBE minus I pi. All right. We want to take maybe a 2A. I'm just going to write this as 2A. And we just want to say that I pi is equals to VBE over R pi. So let's go ahead and plug that in here. So I'm going to go ahead and plug this into here. All right. So then IO is equals to IOE minus GM VBE minus I pi, or minus VBE over R pi. So then let's go ahead and plug in VO for I pi from this equation. So then we get IO is equals to IOE plus GM VO plus VO over R pi. And we can go ahead and solve for IOE. So IOE is equals to IO minus GM VO minus VO over R pi. And so the last equation we want to look at is this loop right here. That essentially says that minus VO, or let me call this 3, or equation 3. So equation 3, let me zoom out a little bit so you can see the other equation down below. There we go. So equation 3 tells us that minus VO plus RE in parallel with RO is equals to 0, or times IO. E is equals to 0, or basically this is Ohm's law that says VO is equals to the resistance RE in parallel with RO times IOE, right? So let's go ahead and plug in IOE. So I get VO is equals to RE in parallel with RO, and IOE is right here. So this equation. So times IO minus GM VO minus VO over R pi. So then VO is equals to RE in parallel with RO times IO minus RE in parallel with RO times GM VO minus RE in parallel with RO times VO over R pi. If I go ahead and move these VOs to the right hand side, what I'm going to get is VO, let me pull out a 1, plus RE in parallel with RO, GM, plus RE in parallel with RO, 1 over R pi, and that's equated to RE in parallel with RO times IO. And essentially now we get our answer, which is R out, which is equals to V out over IO, is then equated to RE in parallel with RO over 1 plus RE in parallel with RO times GM plus RE in parallel with RO times 1 over R pi. Again, for a situation where we consider that the current going in here is extremely small, which is again IB in a BJT. If we consider that to be very, very small, that means that R pi is big. So this R pi goes to 0, so this whole term goes to 0. And so then we're left with R out is equals to RE in parallel with RO over 1 plus RE in parallel with RO times GM. And most of the time, this can be ignored. As a result of this, we get RE in parallel RO over RE in parallel RO times GM, and we can cancel these two. So you're going to see in most textbooks that R out of a common collector is simply 1 over GM. So this is your answer. Okay, so now we'll go ahead and talk about the AV gain, or the voltage output over the voltage input. And so what I did here is I redrew the circuit, and what I'm going to do is I'm going to label some things. So first of all, I'm going to go ahead and delete this VO because it's just the same voltage across here, VO. I'm going to consider RO to be deleted. It's in parallel with this RE, so I'll do that. And then I'm going to consider my currents, that this is IO. There's a small current here called I pi, which again can be equated to 0, but for completion, we'll consider it to be a small current flowing and do the analysis, the exact analysis. And obviously the current flowing here is GM-VBE. And okay, so let's go ahead and write out our first KVL in this loop. So call that loop 1. So we want to first notice that AV is equals to V out over V in. Loop 1 tells us that minus V in plus VBE plus VO has to equate to 0. So VBE is equated to VN minus VO. I'm going to go ahead and write a KCL, including the currents. And I'm going to consider that IO is equals to GM VBE plus R pi, or I pi. Sub to that, I pi is simply VBE over R pi. So let me go ahead and sub this into here, and sub this into here and into here. So then we get that IO is equals to GM V in minus VO plus V in minus VO over R pi. So I hope that makes sense. Let's go ahead and distribute and just keep the term singular. So IO is simply GM V in minus GM VO plus V in over R pi minus VO over R pi. And then the last thing we need to write is a Ohm's law equation based on this VO. And we could say then that VO is equals to RE in parallel with RO times IO. Let me go ahead and substitute IO in here. So VO is equals to, let me consider this RE over IO to just be an A. Okay, so just make things easier. So VO is equals to A times GM, times GM VN minus A times GM VO plus A times Vn over R pi minus A times VO over R pi. If I then go ahead and move my VO terms, this term and this term, to the right hand side, I get VO is equals to, or VO 1 plus AGM plus A over R pi is equated to Vn A times GM plus A over R pi. So then we know then that AV is equals to VO over Vn, which is then AGM plus A over R pi. Again, this R pi is a subscript. And then we get 1 plus AGM plus A over R pi. Now remember, this A is simply RE in parallel with RO, GM plus RE in parallel with RO over R pi. All that is divided by 1 plus RE in parallel with RO, GM plus RE in parallel with RO over R pi. Again, for a situation where the current is extremely small, this R pi becomes extremely big. When I say current, I mean the current R pi, I pi, or the current. This is also called IB, the base current, which normally in BJTs it's extremely small. So this goes to 0 and this goes to 0. This can be ignored. And as you can see, this will cancel out with this. So the AV gain of a common collector or a emitter follower is simply 1. And essentially this is why it's also called the emitter follower. And this amplifier allows us to input a V in and get an output V out, which is just simply equal to V in, because the AV is equals to 1. And there's certain applications where this is necessary and needed, but we won't talk about it in this video. But in videos to come, we will talk about building amplifiers that require the emitter follower. So if you like the video, please give it a thumbs up. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. Please make sure to share the video and also subscribe to my YouTube channel if this was helpful. Thank you.